Okay, good afternoon, everyone. I, Aditya Chandra, along with my teammates, are here to present on the topic Roman concrete. So let's begin. Why Roman concrete? Certainly, Roman concrete is also known as opus cementitium, which was a key architectural material used by the ancient Romans, that played a pivotal role in the construction of their vast empire. Unlike modern concrete, which primarily uses Portland cement as a binding agent, Roman concrete relied on mixture of lime, volcanic ash called pozzolana, and the aggregates such as rubble or gravel. The widespread use of Roman concrete revolutionized the construction techniques in antiquity and continues to inspire engineers and architects today. Understanding the composition and engineering principles behind Roman concrete not only sheds light on ancient construction methods but also offers valuable insights for modern sustainable building practices. Okay, so moving further to next slide, the composition of Roman concrete. So first is volcanic ash, which is one of the most crucial ingredients in Roman concrete. This was basically obtained from the deposits near Pozzoli, which is located in Italy. The second one is lime, which is usually derived from limestone, which is which was the another essential component. The third one is the aggregate. There were various types of aggregate used in this type of concrete, including crust, stones, sand, etc. Now, water is the uh, basic requirement for different concrete. Coming to the preparation of the Roman concrete. Okay, so first step is basically the necessary ingredients are to be gathered, including volcanic ash, aggregates, and water. The second step involves the mixing, which generally involves the mixing together the specific proportions of the selected materials in the required proportions. The exact ratios vary depending on the various factors, such as the required strength of the concrete and the availability of the materials. Third one is the casting. So basically, the casting process took place, then the process is followed by curing. After the placement of concrete, it was allowed to cure and harden over time. This process typically involved keeping the concrete moist to ensure proper hydration of the cementitious material and the development of strength. Now, moving further, some of the key chemical reactions involved in the preparation of the concrete is the hydration of lime, which involves uh, the reaction, which involves basically when water is added, it undergoes hydration, forming calcium hydroxide. Second one is the pozzolanic reaction. Here, the calcium hydroxide reacts with siliceous components of volcanic ash or the pozzolana to form calcium silicate hydrate gel, which is basically a binder material. Then moving on, the third one is the carbonation, which is the generally reaction of carbon dioxide with calcium hydroxide to form the carbonates. The third one is the properties of concrete, which basically involve the durability in marine environment, versatility, self-healing, compressive strength, and environmental adaptability. Now I hand over to my friend Siddhant to explain furthermore about this topic. Siddhant, over to
Thank
you.
you, Aditya. You want to change the slide, please? Can we change to the next slide, please? Yeah. Now it will be coming through in the Roman concrete in architectures. Next slide. No, the previous one, the Pantheon one. On the previous slide, the Pantheon. Yeah. The first Roman architecture coming through in the Roman concrete is the Pantheon. First of all, it's made in the 126 AD. Firstly, it is made as a Roman temple. Now it is being acting as a church. And the striking feature or the trivia behind the Pantheon is that it has the world's largest unreinforced concrete dome, which has an orifice at the top also to provide the light and the rain. Moving forward to the next slide. The next slide is the Colosseum. As we all know about the Roman Colosseum, it acts as an Roman amphitheater in the earlier eras of 76 AD to 200 ADs, where we all have the fights like the gladiator as an amphitheater. Moving forward to the next slide. Next slide, please. Yeah. Now we'll be coming through in the durability of Roman concrete. As we all know, the first property which is being explained in the previous slide is gradual hydration and the curing. The secret behind the durability of the Roman concrete is that it has a gradual hydration process, giving it to the more strength and in the curing process also. The second is the marine environment adaptation. That is, the Roman concrete is highly adaptable to the marine environment as it forms aluminous staubermerite. And the thing is that how does the aluminous staubermerite forms? As we all know, that volcanic ash being present in Roman concrete, as it reacts with the seawater, gradually it forms a compound called aluminous staubermerite, which enhances resistance to the erosions, which makes Roman concrete perfect for the marine constructions also. The third property is the self-healing property. As we all know, in the due course of time, the crack appears in the structures by the rapid environmental actions. So the Roman concrete has a secret property called the self-healing properties also. In the self-healing properties, it forms calcite with its the volcanic ash and the lime and the seawater, which self-repair over time. The coming to the fourth property is the low heat of hydration. As we all know, during the settling property of the concrete, it produces heat, as the reaction is an exothermic reactions. So during the settling of the Roman concrete while making the architectures, there is a low heat of hydration, which reduces the risk of thermal cracking, which contributes to the overall material's durability. Next slide, please. Aditya, can you move to the next slide? Yeah. Now, what are the challenges and limitations of these Roman concrete experimentations that is being done in the recent times? First is the limited samples. As we all know, that according to the World Heritage or the UNESCO World Heritage sites, it is being extremely protected sites for the archaeological surveys. So the samples that is being required for the experimentation or research purposes for the Roman concrete is very limited. So it makes us very vulnerable to use the samples that is being provided to us very meticulously to observe and to produce the experimental results that is being asked to us by the competent authorities. The second is the variation in the composition. As we all know, in the previous era, there is being variation in the compositions, like there is a slight change in the volcanic ash or any other seawater properties based on the locations. Like if a architectural structure is being made nearer to the seashores, then obviously the composition of the seawater must be higher than that of the volcanic ash. So that is why there is a variation in composition which we have to take in account while producing the results or making the graphs. The third is the aging and the environmental factors. As we all know, there is a environmental controversy for the archaeological surveys that is being performed in these World Heritage sites, which deteriorates or damages the age-old sites, which is being preserved by such ages. Coming forward to the next slide. Yeah. Now, what are the experiments on the Roman concrete that is being performed to know much more about Roman concrete by gaining the insights or the results with the certain graphs. that is being handed to us to gain more insights about the Roman concrete. First is the compression test. Second is the acoustic test. Third is the durability. Fourth is the microscopic analysis. Fifth is the chemical analysis. Out of these five, the most crucial one are the microscopic analysis and the chemical analysis, along with the X-ray diffraction analysis that is being explained in the further slide, which will be going through shortly. Yeah, the next slide, please. Yeah. Yeah. Now you can see that as we know, as we listened in the previous slide, that is the microscopic analysis. In the microscopic analysis, we have an analysis method called SEM-EDS. Now, what does it stand for? SEM-EDS stands for small area electron microscopy and electro diffraction spectroscopy. As we here know that it is a microscopic level of analysis that with the help of the electron microscopy, we focus to a certain section of the sample that is being gained to us. As we can see that it is being represented by various colors like the red, blue, and the green, which forms a ternary diagrams, which gives us to the calcium, silicon, and aluminum compositions. As we can see that by the wavelength shift of these chemicals, we can classify it to these colors. And through the ternary diagram, we can see the composition mixture of these samples. As we can see, there is a higher amount of silicon along with the calcium with a lower amount of aluminum in the sample, which has been clearly shown in the graphs. Yeah, next slide, please. Next slide. In the chemical analysis method, which is also a very accurate and prompt method to gain the insights. And coming through the chemical analysis, we have the XRD method. And what does XRD stand for? Is the X-ray diffraction. That is the X-rays or the microwave rays that is being emitted by these samples, which performs diffraction. We able to capture it in the form of graphs, which gives us the further insights about the Roman concrete, like defining the compositions of calcite and the quartz, which proves a key role in the self-healing property and the curing property of the Roman concrete. As here we can also see that while focusing on the microscopic level of the sample that is being gained for us or provide the experimentations, here we can see an EDS cluster that is being shown in the top right corner of the graphs with a blue mark. And also we can see that the red sample, which is in the left part of that, clearly showing the composition of the calcium is much higher in the red portion. As here, calcium is being depicted with the red one, silicon is the green one, and the blue one is the aluminum. And also with the ternary plot, we can see there is a very minuscule amount of aluminum that is being present in the sample, with the majority part capturing with the calcium and the silicon one. As here we can clearly see in the XRD diagrams. Also, the XRD graphs that is being obtained for gaining the insights about the calcium and the quartz is being uh, shown by the spike graphs that is being shown in this graphs as a major phase and the minor phases. Moving forward to the next slide, please. Yeah. Now the comparison between the Roman concrete and the modern concrete, we will be knowing this because that as we come through the Roman concrete topic, we should know that what are the differences between the modern concrete that is being used today by us and that is being used by our ancestors during the Roman era, and what are the differences between these two. As we can see, the Roman concrete, the composition of the Roman concrete is of the lime, volcanic ash, which is also called pozzolana, along with the lime water and the seawater. And also at that time, there is a mix of use with the volcanic rock or brick for the fundamental foundation for the Roman architectures. In comparison, in the modern concrete, we use aggregates such as the sand, gravel, and the water. And also in the cement, we mainly use the gypsum mixture along with the calcium carbonates or the limestones. Another difference is that the Roman concrete offers a remarkable durability and the long-term strength that we can clearly see by the Roman architectures, which we shown in the previous slides, like the Pantheon and the Colosseum, which stands the test of time by standing tall up to 2000 years long. And we all know the lifespan of the modern concrete as it merely have a lifespan of 10 to 15 years, which also depends on the performance, and it can vary on depending on the mix designs and the curing conditions and the exposure conditions that is being thrown to the modern concrete structures. Then also by excellent mix design also it can slightly move forward to 20 years of lifespan. And coming to the third difference is that it has a lower carbon dioxide emissions, while in the modern concrete there is a significant amount of carbon dioxide emissions while the settling of the Roman concrete. Coming to the fourth difference is that the use of volcanic ash improve the workability, that we can mold it to any shapes and sizes, and showing us to the great moldability and the workability of the concrete. Coming to the modern concrete is that it also offers excellent workability and can easily mold it into various shapes. Now I'll be giving the chance to my friend Shweta Padma to move forward to the next slide, please. Thank you.
Thank you, Siddharth. Moving to the next slide. Aditya, please change the slides.
So I have changed the slide. Is it visible?
Okay. Next slide includes environmental impact of Roman concrete. Roman concrete production generates carbon dioxide emissions due to energy-intensive process involved in lime production and hot mixing. Use of Roman concrete in marine structure includes habitat disturbance and long-term effect on marine biodiversity. Next slide, please. Okay, here we are concluding that the research finding mainly focuses on the intricate process governing the evolution and composition of ancient Roman cementitious materials. The previous evidence suggests that in ancient Roman cementitious structure, the relict lime clast can react over time with the other mortar components forming amorphous, for example, CSH, and crystalline phases like aluminum tobermorite, and stratlingite. While the present study confirms clear inclusion of silicon and aluminum in the lime class, suggesting that some conversion to CSH like calcium carbonate, predominantly calcites, remain within their pores. The investigation sheds light on the role of water availability, indicating the reaction kinetics and evolution of different mineral phases. Moreover, the research highlights the self-healing potential of lime clast containing concrete, suggesting a mechanism where cracks are filled by calcium-rich phases leaching from the lime clast, ultimately contributing to the long-term durability of ancient structures. The findings deepen our understanding of ancient structure practices and offer insights into the development sustainable cementitious material for modern application. Next slide, please. Here, there are the references we referred for our slide preparation. And here we are concluding our presentation. Thank you so much.
Thank you, everyone. This is all about our presentation. Here is this small references which we used. Thank you.